Now, the first thing we have to do with such a discretisation is check that it is indeed consistent with this partial differential equation. But rather than work from here, let's work from this step and the PDE, because of some rather beautiful things we can use. Okay, so substitute this into the PDE, and the left-hand side we can recognise is 1 over tau times the centred difference acting on u, j, l plus a half, because if you look at the centred difference in time acting on that, you'll get precisely this. What about the right-hand side? Well, the right-hand side is, for our discretisation, is k times uxx, and uxx is a half of the centred difference squared, that's delta x squared uj l divided by the h squared, plus the same centre difference at time l plus 1, plus delta x squared uj l plus 1 over h squared. Now, the common factor of h squared, so bring that out the front as a denominator, multiply both sides by tau, and then what sits here is k tau over h squared, which is the parameter s that we used over here. Right, so delta t u j l plus a half is equal to s into a half delta x squared u j l plus delta x squared u j l plus 1. Now, we've seen this combination before of a half of something at a discretisation L plus something at a discretisation L plus 1. It's the mean operator in time at L plus a half. Right, so this is S times the mean in time of delta x squared uj L plus a half. Right. So now this is our equation that's equivalent to the discretisation, and to write this as an operator equation, we just factor out the uj L plus a half that's on both sides, i.e. delta t is equal to s mu t delta x squared. Now, it's convenient to put all the time operators on the left, so divide by mu t, and you get that equation. And our discretisation is, in some sense, equivalent to this operator equation. All right, now what do we do with this? Let's try and write it in terms of more familiar operators, such as the shift operator in time. So, delta t is the shift operator to the half minus the shift operator to the minus a half. Mu t is the shift operator plus the shift operator to the minus a half divided by 2. This has to be s delta x squared. Multiply top and bottom by the shift to the half, so that we get ones here and ordinary thing there. And then multiply the top and bottom by 2, and then, well, and do the same, and then we get it. Well, this division by a half is multiplication by 2 in the numerator, so divide by it and we get a half on the right-hand side. So let's do both of those. That's et minus 1 over et plus 1 is equal to a half s delta x squared. It's an s. Now, rearrange this for the shift operator ET. So multiply by ET plus 1, and this is S over 2 delta x squared ET plus S delta x squared over 2. Right, now move that ET to the left and that minus 1 to the right, and the left-hand side becomes ET into 1 plus S delta x squared on 2. Sorry, that's a minus. And the right-hand side, when that 1 goes over there, is 1 plus S delta x squared on 2. Alright. Now divide by that, and we get the shift E in time is 1 plus S delta x squared on 2 over 1 minus S delta x squared over 2. Now this is still in terms of shift operators. We can turn them into derivative operators using these relationships. So for example, ET is e to the tau d by dt. So d by dt is 1 over tau times the logarithm of this right-hand side. So d by dt is 1 on tau log. Now what's this right-hand side? Delta x squared is 2 hyperbolic sine h dx on 2. So square that, that's 4 sine h squared. Divide by the 2 is 2 sine h squared. So it's 1 plus s times 2 sine h squared h dx on 2. And the denominator is 1 minus exactly the same thing. 2 sine h squared h dx over 2. Right, and the consistency or not follows from Taylor expanding this in h, because consistency is what happens with this discretisation as the grid spacing h goes to 0. So we're interested in small h approximations of that. Alright, so computer algebra will easily derive the Taylor series for this. So I leave that for you to do. And what you find upon computing the Taylor series on the right-hand side is the following. It's the right-hand side is 1 over tau s h squared d by dx squared plus 1 over tau s h to the 4th over 12 d by dx to the 4th plus order h to the 6th. Now we simplify this a bit because sh squared over tau is the diffusion constant k. So this is k d by dx squared. Similarly, sh to the 4th over tau is k h squared. So this term becomes k h squared over 12 d by dx to the 4th plus those higher order terms. Now this operator equation is somehow equivalent to the discretisation, and what it means is the discretisation is equivalent to this operator acting on a function u of xt. So the equivalent PDE of the Crank-Nicolson scheme is du by dt is k u xx plus k h squared over 12 u 4x's plus higher order terms which we haven't identified. Now this equivalent PDE is great. What we have here is the original diffusion PDE. That's marvellous. And what we have here is the error, and in particular this term is the leading error. And key feature about this leading error is it's got a coefficient of h squared in there. It's of order h squared. So as the size of the discretisation h goes to 0, these errors will go to 0, leaving the equivalent PDE being just the original PDE that we wanted to solve. And that implies that the scheme is consistent, which is one part of the necessary requirement we need.